Greetings, Panthers. Welcome back. Part 2 of this video on solution stoichiometry, and this time we're going to look at what's called volumetric analysis. The first video, if you haven't watched it, deals with gravimetric analysis, mass amounts measured, and then using principles of stoichiometry to figure out masses in a solution. The second is volumetric analysis. This uses volumes and concentrations. So this is a classic example. You haven't quite covered acid-base reactions yet, so there's other videos on acid-base reactions and another one on titrations, but this is sort of your first introduction to this. So we have a base, sodium hydroxide. It reacts with sulfuric acid, and the general reaction scheme for acid-base reactions are acid plus base yields salt plus water. And when we say salt, we mean an ionic compound, not necessarily NaCl, although it could be NaCl. So an acid plus a base is a salt plus water. Acid is something that has an H plus ion. Base, often in this case, will have an OH minus ion. So it's an H plus ion plus an OH minus ion, yielding salt plus water. So sodium hydroxide is NaOH. And sulfuric acid is H2SO4. These are some of the acids and bases you're supposed to know the formulas for. And you notice the products are sodium sulfate and water. So let's write out every time you do a stoichiometry reaction, whether it's in solution or whether it's in the solids or gases or whatever, you always need to write out the balanced equation. So let's start with our balanced equation, and we'll just be consistent with the ordering of the wording in the problem. So NaOH aqueous plus H2SO4 aqueous yields sodium sulfate, Na. Sodium is a +1 ion, sulfate is a 2- ion, so that has to cross down. Next section, you're going to learn the solubility rule. Sodium sulfate it dissolves in water, so it's aqueous, plus H2O liquid. Then the next thing we need to do is balance this equation. Just quickly using our rules, we noticed that there's 2 of these and only 1 of these. So I'm going to need a 2 out in front of the sodium hydroxide. And I've got 1 sulfate, 1 sulfate. So this is not going to need to change. So I'm going to need to put a 2 out in front of the water to balance this equation out. The key understanding is there are 2 moles of sodium hydroxide for every 1 mole of H2SO4. Okay, that's that special stoichiometric ratio. I'll even write it down here. 2 moles NaOH for every 1 mole H2SO4. That's going to be the key factor which lets me change from one species to another. I do this a little differently than most of the books do it. So if you follow my logic here, you'll see kind of how I approach this problem. So when you look at these problems, there's always some kind of similarities to them. One of them will have enough information. One of them will have a volume and a molarity. So it says, suppose a beaker contains 35 milliliters of 0.175 molar H2SO4. Whenever you have a molarity and a volume, you can find the number of moles, and you do not need the molecular weight. So the question is, how many milliliters of a different molarity sodium hydroxide solution must be added to completely react with the sulfuric acid? So the general strategy is I want to find the number of moles of H2SO4. And remember, I can use molarity times volume will equal moles. Then I'm going to use the balanced equation to convert to moles of NaOH. Okay, that's this relationship here, 2 moles NaOH for every 1 mole of H2SO4. Then, once I know the number of moles of sodium hydroxide, then I can find the volume of NaOH. And I can find the volume because I know that the number of moles of NaOH is equal to the molarity of NaOH times volume NaOH. And the way these problems are set up, they're always going to end up this way. You're going to have moles of whatever the other titrant is, and you're either going to be given a molarity or you're going to be given a volume. So depending on how the problem's worded, you either have to find the molarity of that unknown acid or base, or you're going to have to find the volume. In this case, we're asking for how many milliliters, so we're looking for volume. But from this equation, number of moles equals molarity times volume, you can figure out either type of problem. So let's take a stab at this problem right now. I'm going to write down the information I have. My volume of H2SO4 is equal to 35 milliliters. My molarity of H2SO4 is equal to 0.175 molar. My molarity of NaOH is equal to 0.250 molar. And my volume of NaOH is what I'm looking for. Now, some of you in high school may have learned molarity acid times volume acid equals molarity base times volume base. I want you to be careful with this equation. This only works if we have a 1-to-1 ratio of acid to base, something like HCl and NaOH. Okay, so this is not a generally valid equation. This only works for specific cases. We already said this is a 2-to-1 ratio, so therefore we cannot use this equation, which you might have learned in high school. Okay? And just generally speaking, in my classes at least, you're probably not going to see one of those because you can not understand how to use this stoichiometry equation and still get the right answer. And I want you to make sure you understand how to use the stoichiometry equation. So let's start off, let's find the number of moles of H2SO4. So number of moles of H2SO4 is going to equal to volume times molarity. 35 milliliters times 1 liter per every 1,000 milliliters. That's going to cancel that. Times 0.175 moles H2SO4 for every 1 liter of solution. Liters of solution is going to cancel liters of solution. So I'm going to get a number of moles of 6.125 times 10 to the minus 3 moles H2SO4. And I'm just going to keep, I know the sig fig rules, and I know that I've got one extra, but because that's a 5, I'm just going to hold on to that one until a little bit later, because that we'll see if it rounds up or down. Okay, so that's my number of moles of H2SO4. So that takes care of step 1. Step 2, I need to find the moles of NaOH. Moles of NaOH is going to equal to 6.125 times 10 to the minus 3 moles H2SO4 times, now here's that key stoichiometric ratio. Here's the 2 moles of NaOH for every 1 mole of H2SO4. That's where that's going to come into play. So I need to put H2SO4 in the bottom, so 1 mole H2SO4 for every 2 moles NaOH. Moles H2SO4 cancels moles H2SO4. So that is going to equal to 1.225 times 10 to the minus 2 moles NaOH. And once again, I'm just going to keep an eye on this extra decimal here. I know it should have 3 sig figs. It should have 3 sig figs because of the volume that we started with is only 35.0. But I'm just going to carry 1 extra decimal down through the rest of my calculation. Okay, so my last step, so that takes care of step number 2. My last step is find the volume of NaOH. And this is where I do things a little bit differently than the way the book might do it. And hopefully this simplifies it a little bit. So this is equal to number of moles NaOH. But we know that that's equal to the molarity of NaOH times the volume of NaOH. Okay, that number is the number of moles of NaOH, and that's equal to molarity times volume. Molarity times volume always gives you number of moles. So we go back and look in the problem, and we recognize that I'm looking for how many milliliters, so I'm looking for volume. So I don't know this one, so I'm going to rearrange this equation. VNaOH is going to equal to N, little n, NaOH number of moles, divided by molarity, NaOH. Okay, so then it's just a simple, it's a simple math problem now. NaOH, I'm just going to plug in 1.225 times 10 to the minus 2 moles NaOH, divided by the molarity is 0.175 moles. I'm going to write the whole unit out for molarity just so you see. Moles NaOH per 1 liter of solution. Okay, and then moles NaOH is going to cancel moles NaOH. This is going to equal to 0.0490 liters. But my problem was actually asking for milliliters. How many milliliters? So I need to convert that. So volume NaOH in milliliters is going to equal to 0.0490 liters times 1,000 milliliters for every 1 liter. Liter cancels liter. And that is going to equal to 49.0 milliliters of NaOH will be required to try to titrate this H2SO4. So of my 0.25 molar NaOH solution, I'm going to need 49.0 milliliters of it. And we do have 3 sig figs here. I'm going to need 49 milliliters of it in order to completely titrate this reaction. Again, this is a little bit different way than the book does it, than most books do it, with this little relationship right here, number of moles equals molarity times volume. But this allows you to solve for any type of problem, whether you're looking for volume or molarity. And I kind of like to get it down to this step and then solve it. Key thing though, this is a 2-to-1 ratio. You cannot use this equation you might have learned in high school. You need to remember that mole ratio of 2 moles sodium hydroxide for every 1 mole of H2SO4. If you do that and forget this equation that you learned in high school, you can solve any acid-base titration problem. All right, thanks for watching.